You do 47, please?
Absolutely. Okay, so 47 says the selectivity of chlorination at primary, secondary, and tertiary carbons is about 1 to 4 to 6, a ratio that's relatively independent of the type of most solvents. If the reaction takes place in benzene, however, it is believed that chlorine, Cl2, forms a weak complex to the aromatic ring, thereby stabilizing the chlorine molecule. Does this lead to a greater selectivity or a lesser selectivity in chlorination? Explain. Okay, so in order for us to actually have the reaction occur, the first step is that we take a chlorine and we go through homolytic cleavage. So we'd have one piece go over to this side and the other piece go over to this side. That will give us 2 chlorine radicals, and that's the rate limiting step. So we have those 2 different pieces. We're going to have this be rate limiting, and it would be much more favorable to go back. It's just we have more of the reactant than we have the product. If we think about that, these are both higher energy, and so we look at the reaction coordinate like this, right? We're going from Cl2 to Cl radical. And the Cl radical is much higher in energy, so we have an endergonic reaction. When we react it with benzene, it's saying that we're making the Cl2 more stable, and so that's making this go down. That means it's going to take actually even more energy to react to make that chlorine. So far, so good?
Yeah.
Okay.
Yeah.
So if it takes more energy to make this chlorine, then we're going to have probably excess energy in the system. And when it goes down, eventually to react to form the new bond, we're going to be pulling off some sort of RH, a bimolecular homolytic substitution. Or let's see, so we end up, let's see, not that way, this way. So we end up with the radical, and the radical is going to be stabilized depending on whether it's primary, tertiary, or secondary. So, the primary is going to be the least stable. We'd have more stable secondary and more stable tertiary. So far, so good? Can you see that okay? So the idea is, if we have decreased this energy, it's going to take us more energy to get up here. And so we're going to have a lot more problems trying to get just to stop here because we've already put in extra energy to make up this gap difference when we have Cl2 complexed with benzene. So because we have to put in that extra energy initially, then we have extra energy as we go through the reaction, and it makes it a lot harder to selectively end up right here. Selectively end up here instead. Each of these will have their own eventual peaks that look kind of like this. They'll all end up with fully, not radical substituted products eventually that have similar stability. So it's this step that really matters. And when you have excess energy at the beginning, it makes it harder to stop at that step. Does that make sense?
Yeah, thank you.
Yeah, no problem.